Welcome everyone to week 6. I'm happy to see you all alive and well after quiz 0, because I know that was a bit rough, but thankfully you all did incredibly well, and so that is wonderful. I've handed back, if you're in my section, I've given most of you back your quizzes already. A couple of you I'm meeting after class, and if you're an extension student and you haven't received your quiz back yet, your TF is probably working on it and grading it, and we'll get it back to you shortly. So my extension students who are watching right now, hopefully live, I will get you your quizzes shortly as well. Our agenda for today is as follows. First, we are going to go over some resources that CS50 provides to you. We're going to go over quiz 0 next, and I will answer any questions anybody has about particular problems. And then we will be going over file IO and problem set 5. Those last two topics will take up the bulk of section today. I put this list up every week as a reminder to you all, but of course, section, we only have 90 minutes. We aren't able to cover everything that I would love to cover for you guys, but we do have a ton of resources for you to draw upon as you get to know the material and work through your problem sets. A reminder that I have online a text box set up for you to fill out if you have any feedback for me, both positive and constructive, about section. That URL is located right down here. So please take a moment if you have any feedback, whether during section or after you watch the video online, to give me your feedback. I really appreciate any and all of it. So I've been having small conversations with a lot of my students throughout the week as I hand back quizzes, talking about the course, seeing how you're doing. And one theme has come up over and over in talking about, in particular, problem sets. And I have epitomized or encapsulated that theme on the board right now. Essentially, there's a difference between turning in something that is done correctly and something that is done well. Most people have been doing fantastic in terms of correctness, 5s or 4s on all P sets. Most people are getting those all of the time. However, just because you have done something right does not mean you've done something as elegantly or efficiently or as cleanly as you could have done it. And that's what the design and, to a lesser degree, style axes are for. So I am pushing you all, and other TFs are pushing you guys to not only turn in things that are correct, but turn in things that are coded well, not doing unnecessary for loops, not recalculating variables if you don't have to. For example, looking back to problem set 4, when placing the bricks on the screen, every brick in a given row has the same y coordinate, the same height coordinate. So that y coordinate did not need to be calculated inside the interior nested for loop that you likely used to put those bricks on the screen. It only needed to be calculated every time you switched a row or moved down a row. So say if there are 10 bricks in a row, each brick can have the same y coordinate, and that y coordinate can just be calculated once for all of those. It does not need to be calculated 10 times. Nor does that calculation need to happen in the actual function call, the new grect function call. So if that was a little confusing for you, more generically, things that don't need to happen every single time you go through a for loop shouldn't be put inside the for loop and shouldn't happen every time you go through the for loop. Another good design example we saw in week 3 for 15, you could keep track of the 0. So when you initialize the board, you save in a global variable, perhaps, the x and y coordinate of the 0. And then whenever you, in your move function, whenever you make a successful move, you update the location of the 0. That would save you from having to do nested for loops to look through the board every time in your move function and find the 0 or find the tile and then check what's next to it. Instead, you have the location of the 0. You can just look above, below, and to the left and right of it to find what the tile you were looking for. So in terms of the programs we're writing, they're never large enough that some of these design decisions are really going to hamper your program or make it run more slowly or perhaps even run out of memory. But we're still pushing you guys to write as elegant and efficient code as possible. So if you do end up writing things that have a significantly larger scope, they will be written with good design in addition to being correct. So a number of you have brought that out. That's something we're looking for, something we're going to continue to push you guys on. And if you have any questions about the design of your program, feel free to reach out to me, and I'm happy to walk through your program with you and point out some of the design decisions you made and give you some suggestions on how to make even better design decisions. So we're going to move on to talking about Quiz Zero. Before we do that, does anybody have any questions about what I've covered so far? Seven seconds. OK, let's talk about Quiz Zero for a bit. Most of you have your Quiz Zeros back. If you don't, you have hopefully remembered a bit. But if you've taken Quiz Zero, then you also have access to the PDF online and the sample solutions. Does anybody have any questions before we jump into the week's material about a particular problem on Quiz Zero, why the answer is what it is? Is anybody confused about anything? Even if you got the problem right but just would like me to explain it a bit more, I'm happy to do so now. So hope I have asked you guys to come prepared with some thoughts about Quiz Zero. So who would like to get us started with a question or comment about Quiz Zero? Not everybody did perfectly, so I know there have to be some questions about Quiz Zero. OK. Yes, Apika.
Number 10.
Number 10. Which one was number 10? I have it.
Include.
Number 10 was A to I, writing A to I?
Yeah.
OK. So another question you could have asked was, am I prescient? The answer is yes. In section before the quiz, I asked you guys to code both Sterlen and A to I. Both of them happen to appear on the quiz. So hopefully you paid attention to that. And if you had, then you would have probably done well on those two. But A to I, we didn't actually code it in class. But it was, again, asked on the quiz. So a couple of things to take note when coding A to I. The first thing per the question was that you needed to check if the string was equal to null. A couple people tried to check later on in the program if S bracket I, so a specific character in that string, was equal to null. But remember that null is essentially, it's good to think of null as a pointer, as a 0 pointer, a pointer to 0, some place in memory where you can never access. So if something's equal to null, you know that it hasn't been initialized or there's nothing there. So S itself is a char star. S bracket I is a char. So it makes sense to compare S to null, but not S bracket I to null. But again, so that was the first thing that you were supposed to do. Check to make sure that you actually got a real string. Next, you wanted to go through each character in the string. And so that would be like an S bracket I, for example, if I is your iterator. And take that character and get its actual value. You have it stored as a char, but the ASCII value for 0, 0 as a character is not actually the integer 0. It's some other number that you can look up in the ASCII table. So one way to correct for that, probably the best way to correct for that, is subtract from it the character value, or 0 as a character. So minus single quote 0, another single quote. That'll take whatever number you have as a char and get it equal to the number as an actual integer. And that is very similar to what the approach a lot of people took in problem set 2 with Caesar and Vigenère, those ciphers, when you were rotating them. So after you have it as a number from 0 to 9, then depending on where it goes in the ultimate number, you need to multiply it by a power of 10. Some people move from the back to the front and multiplied the individual number by a power of 10. Some people moved from the front to the back, and so took the highest order numbers first, and would save those in a global counter variable, and then each time through the for multiply that giant global counter variable by 10 to make space for the next char. So that was a little confusing without me writing it on the board, but the sample solution is available to you. But those were the big things we were looking for. Also a check to make sure that each individual character was indeed a character between 0 and 9 and not some other character like an A, for example. So those were the things we were looking for in that question. Does that answer your question?
Yeah.
OK. Are there any other questions about Quiz Zero? What about compiling? Everybody compiling right? No. There were a lot. Any questions about the compilation process? Wow. Yes, Michael.
Number 7, random.
Number 7. Number 7 was get a random integer. Excellent. So you're given an integer a and an integer b, and you want a random integer between a and b. We can actually write this one on the board because this one was one line of code, one way to do it. So we're given drand as a function we could use, and what is drand? Assuming it's been seeded, what does drand return?
A float between 0.0 and 1.0.
A number between 0 and 1. And so we have b and a, and then we have a random number between 0 and 1 given to us by drand. Some people tried to put b or b minus a or something inside those parentheses. That would mean that they're arguments to this function. drand does not take any arguments, like getString does not take any arguments. So it's just open paren, close paren, and that itself is the function call, and that gives you a number between 0 and 1. Of course, we have a whole range that numbers can be in. Say if b is 10 and a is 5, we really want a number with a range of 5. So the next thing we need to do is multiply this by the range b minus a. So assuming that's multiplied, and that'll give us a number within a given range, and that specific range being the difference between b minus a. And finally, that'll only give it from, say the range between b minus a is 5. That'll give us a number from 0 to 5. But if a is in fact 5, we need to boost this range up to where it's actually supposed to be by adding a. So that gets the logic right. And then, do you have another question?
No, I just feel really dumb right now.
Don't feel really dumb. A number of people struggled with this question. And then the other question is drand, you said gives you a float, returns a float, but this function actually asks for an integer to be returned. You don't need to cast this explicitly to an integer because these operations will treat it as all float, as a floating point number. Like this will, even if this is an integer, this will be multiplied correctly. All the multiplication will work. You don't need to cast it here. In fact, you shouldn't cast it. That would, if you cast a number that's between 0 and 1, a random number, a floating point, then it'll either be only 0 or 1. So you lose all of that precision. But at the end, when you return, it automatically gets sent back as an integer. So you don't need to do that casting yourself. So this was the answer to that question, number 7. Any other questions on quiz 0? Yeah, Annie?
When do we use recursive? Like when do we use iterative, like loops?
When do you use recursive? So more generally, the pros and cons of recursion versus an iterative approach. Can anybody offer a pro or a con, please? Not can anybody. Who can offer a pro or a con?
Recursive is less coding, less typing.
So generally, recursion, especially a function or an algorithm like merge sort, which lends itself to a recursive approach, might be more straightforward to code recursively and just make more sense to do it recursively. So that would be a pro to recursion. Others, yeah?
Con to recursion? It uses more memory.
So exactly right. A recursive function will keep adding stack frames to the stack. So if you're operating on a lot of numbers and have to call this function a lot, then you will certainly take up more memory, while an iterative approach will only put one stack frame on the stack because it all happens within one function. Any other pros and cons? Yeah?
Pros for recursion, you don't have to determine in advance how many times the code has to be repeated. Like if you have a predetermined number of times that you have to iterate, then recursion is better because it takes care of itself.
I think that's true, but I think in both cases you would never, you would probably get some input from the user, or this function would have some input that would determine how many times it should run. So generally you wouldn't hard code, even in an iterative approach, how many times that loop should be run. Did you have another you were thinking about, Annie? Okay, so those are probably the two, the biggest pro and the biggest con to a recursive versus an iterative approach. Okay, anything else on quiz 0? Let's move on. File.io. There is a wonderful short this week on File.io that hopefully you have watched multiple times and admired. A lot of work went into that, and I've heard it is insanely helpful. I also included the link on this slide in case you have not had a chance to watch it 10 times. So we are going to briefly go over the major steps to opening and working with files, and then we are going to dive into a coding problem before examining the problem set. So again, I'm going to put this up on the screen, but I'm going to talk for just a minute about what we are doing here with File.io. What does that mean? That means that we can create our programs and then have our programs exit and not have made any impact on the world outside of our program. But when we start working with files, both reading them in and creating them, we can have some effect on the world outside of our program. Just like if Microsoft Word wasn't able to make any Word documents, then once Microsoft Word quit, all of your work would be gone, and it would really be useless. We do ultimately want to be able to write programs that can affect the world around them, both by taking in complex inputs in terms of files and via files, and also creating interesting and compelling outputs in terms of different types of files. So that is why we are starting to learn how to work with files. More specifically, what we do is as follows. It's very simple. There are only a couple of steps, and they are listed here on this code. So we're going to go through this code line by line. First, you see highlighted when you're working with a file, regardless of the type of file it is, you need to open it. And that is with a call to fopen. Right here, you include the name of the file. If the file is not in your directory or the folder where this program lives, then you also need to include a path to where that file is. We're going to assume that this file called text.txt, a simple text document, is in the same folder as this program is. So that's another thing to keep in mind, that if you want to open a file somewhere else, you actually need to include its location. Second, you can pass an argument to fopen, and that's what you want to do with the file. There are three main arguments that you're going to pass to fopen. Who can give me those three? Who can give me one of them? Yes?
File name.
Sorry, three main arguments you can pass as the second argument to fopen. You're right, the file name is the first argument, but the second argument to fopen are generally three strings, and yes, Aleja.
A for append.
A, if you want to append to a file that already exists.
R for read.
R, if you want to read from a file.
W for write.
And W, if you want to write to a file. So in this case, we're writing to the file, so we have W. You open it. You also have to save the file somewhere, and that's with the code to the left-hand side of the assignment operator. I'm creating a pointer to a file called, in this case, file. We are not going to worry what this all caps file thing is. Suffice it to say, it is a long stream of zeros and ones, and that's how we are going to operate it and understand it. The next thing we need to do, and this is incredibly important, whenever you open a file, in fact, whenever you call malloc, for example, and get some memory and try and save it in a pointer, you always want to check to make sure that that function did not return null. So in this case, we are checking to make sure that we actually opened the file correctly and there was no error in our program. Next, once we've checked to make sure that we have a working file, we can write to or read from or append to the file. In this case, I am simply printing one line to this file. How do I know that? Well, I'm using this function called fprintf. All of the functions you will be using when writing to or reading from or manipulating files will be similar to functions you've seen before, but start with the letter F, standing for file. And fprintf, unlike our normal printf, takes one additional argument, and that is the file where you want to print this line to. I don't have anything to the right of ohio. I don't have the third argument to printf, or the second argument to printf, the third argument to fprintf, because I don't have any placeholders here. I'm not including any variables. But again, fprintf and all of these file functions that operate with files are generally going to need the file on which they're operating. Finally, the last important thing to do is to close the file. Just like with whenever we malloc something, we want to free something, lest we have a memory leak, we want to close our file. If this program exited without closing the file, odds are nothing would go wrong, especially if it was a small file, but it is certainly good coding style and practice to always close your file when you're finished using it. So that is the basics of File I/O. You've probably seen that before or watched it in that fantastic short. Does anybody have any questions before we go into some practice coding problems about File I/O or the steps I just went over? Do you have a question, Avi?
No.
Okay, I'm going to wait another 7 seconds. That's a really good tip. You guys just don't like asking questions. That's fine. Okay, so our first practice problem is we are going to duplicate the function of a command line tool that you have probably used before, copy, the copy tool. If you type CP and then pass it 2 arguments into your terminal, you can copy a file. And that is what we are going to write right now. So again, reading off of this slide, I'd like you to write a program that takes 2 and only 2 command line arguments, a source file and a destination file, and copies the contents of the source file to the destination file 1 byte at a time. So that's a lot to ask for. Again, a good approach to this is to not go straight to the C code, but break it down into a couple of steps. First, think about the logic, exactly what I am asking you to do, and understand all of the steps to this problem, not in C, just in some pseudocode, or even a mental model of what's going on. Next, once you have the pseudocode down, figure out how the pseudocode maps onto tools and things we've learned to use in C. And finally, once you have all that together, you can code the problem. Take 5 to 10 minutes to work on this problem. I'll put the instructions back up in a second. And then we are going to go over the pseudocode and code it live as a group. If you have any questions while you're working on this, feel free to raise your hand, and I will come around and answer them. One second. Okay, let's go over the pseudocode first, and then I'll give you a couple more minutes to finish coding. Who would like to start me off with the first line of pseudocode for this function?
Check to make sure that you were given 2 files.
Okay. And if we're not,
Return 0.
should we return 0?
Return blanking. Sorry.
Yeah, probably not 0.
Yeah.
Because 0 means everything was good. Okay, so that's the first line of pseudocode. Who has the second line of pseudocode?
Can open both the files.
Open both files. Okay.
Check to see if the file's null.
Check to make sure neither are null. As an aside, /0, is that null?
No.
That's not null. That is called the null terminator. It's actually spelled with only one L. So checking something against that, that's actually a character. So checking something against that is not the same as checking to see if it equals null. And some people on their quizzes and their problem sets have got the two of those confused, but the two of those are in fact different. One ends a string, one is a pointer to 0.
Why wouldn't you check to make sure that the files are null or not null before you open them?
So open returns, save something in that file. If we go back here. So this line, fopen, will save or give you an address and store that address in file if it works.
Okay.
If it doesn't work, it will store null in
Yeah.
file. So you can't check for null before you've opened them. Null means something didn't work correctly. Okay, so check to make sure neither is or are. What do we think? We'll go with it. Is? Neither is?
Is.
Okay, seem to have some consensus on that. Neither is null. Okay, next line of pseudocode. Who hasn't given me a line yet? We will wait for you. Yeah.
You have to read from the first file?
Okay.
Or you use fscanf or something like that, the first file?
So we want to read from the first file, and let's put that right here. Read from the source file, and then what do we do after we read from the source file? Somebody else?
Write into the destination file.
We write to the destination file, and okay, what else are we missing? Somebody else who has not given me a line of code yet, of pseudocode. Yeah.
Maybe you can always check like whether there's something to read from, like the next line, whether like the next line still exists.
Oops. That's my journaling software. Yeah?
Yeah.
So give it to me one more time.
Check whether there's still a next line from the source file to read.
Okay. So we're not reading lines, we're reading bytes here.
Okay.
But you're correct. We want to read and write until there are no more bytes. Okay, and so these should really be indented a bit because they're under there, right? Until we're out of bytes, we're going to read from the source file and write to the destination file.
Yeah.
And then what is the last line of pseudocode? Someone who's not given me something yet.
Close the file.
Exactly. Close the files. So there's our pseudocode. I'm going to put the pseudocode into gedit, and in a couple of minutes we will code this together. Okay, let us get started as a group. Nishant, I have my new file. I just opened this up, untitled document 1. What's the first thing I should do?
Include libraries.
Okay. What libraries?
Standard.io.h, standard lib.h, I believe.
Okay, what is standard lib for?
I forgot.
Okay, so we'll include standard.io. What should I do even before I start coding?
What's your name?
Write a header.
How do I get it colored?
Save as a .c. How do you get it colored?
How do I get color coding?
I don't know. Well, save.
Save. Yes, I should save it as a .c. So save it on the desktop as cp.c. Sweet. And if I want to get full style points, what should I include at the top?
You could write the name, your name, name of the program, and the purpose of the program as well.
Looks good. Excellent. So you've started us off perfectly. Sharp include will also write. Okay, so I think I am all set to go. Who has the first line of code for me? Or the first lines of code that it will take to satisfy our first comment in pseudocode? You.
Should be between int argc and then char star brackets.
I think you're right. Let's change it to int made open paren int argc comma char star argv, like that. Brackets. Open bracket, close paren. Perfect. Now we can take command line arguments. Okay, ensure we're given 2 files. You can give me that as well.
And then if argc does not equal 3.
If open paren argc does not equal 3.
Yeah, return 1 or whatever.
Sorry?
Return 1 or anything.
Return 1. Okay. Great. Open both files. Who can help me open both files? Who hasn't given me code yet? Kurt.
So all caps FILE star source.
I'm going to take out the vowels.
Sure.
Because we're cool. It's like Tumblr.
Right. Equals F open.
Equals F open.
Open paren argv open bracket.
Wait, sorry. Open paren. Okay.
Yeah. Argv sub 1. Right?
Sub 1.
Yeah, argv like open bracket 1. Yes. And then comma, and then open double quote r double quote close paren semicolon.
Sweet. And what about the other one?
Very similar, but instead of src, you call it like dst.
Ooh.
And
I like that.
Just dst, yeah. And then argv sub 2 or argv open bracket 2, yeah, and then w instead of r, yeah.
Great.
Cool.
Next couple of lines. Also, if anybody has things to add to lines that we've done, feel free to add those as well. Check to make sure neither is null. Who can give me the code I need to do to write that or satisfy that line of pseudocode? Akshar.
If src equals null, or dst equals null, then you return
What?
return 2.
Return 2. So if open paren src equals null or whatever that thing's pipe, we'll call it pipe. Pipe, dst equals null, return 2. Okay? Until we're out of bytes, we sort of skipped over the step from the pseudocode part to going to here, but until we're out of bytes, what does that sound like? What type of C structure, but I don't want to use the word structure because we're going to start using that in other cases, but C tool does that sound like? A loop. Sounds like a loop. So who can give me this loop, the first line of the loop code right here? you can also pick what kind of loop you want if you give me this line of code. There are 3 kinds you get to pick. I would suggest one of those. Avi, which one do you want?
4.
4.
Int I equals 0.
Okay.
This part I'm not sure about, but I is less than size of star source. I'm not sure though.
Okay.
Because you want the size of the file, right? Or like,
So this probably won't give us the size of the actual file in bytes. So what else could we do? What is another type of loop, or should we stick with a for loop?
Could you do a while loop? And
Okay.
then what you do is if because we have a char star for the file, so if we just keep incrementing that until we find the null character at the end of it, or no, is that not how files work?
So we can keep incrementing the char star until we find the null.
Essentially, keep going character by character until we hit like the end of the file.
Yes, so that's what we want to do. We want to keep reading character by character until we get to the end of the file.
Yeah, but I'm not sure. Like, what's like the end or stop sign at the end of a text
Okay, so
file?
when we get to the end of the file, how do we know we've reached the end of a file? If I am calling, so let's step back. What is a function? Let's go to this line right here. Read from the source file. Who can give me that line of code?
fscanf.
Fscanf. Okay, what if I want to read very specifically 1 byte?
I don't know.
Okay, even simpler than fscanf, what is I want to read from a source file? Read from a source file. What is a function? Yeah.
Is fread?
fread. I think let's stick with that one for now. What kind of arguments does fread take?
Probably the file type and then location within the file.
What can I type here to figure out what type of arguments fread takes?
And fread.
Man, fread, fwrite. It looks like they hang out together. So fread takes how many arguments?
And mem.
It takes 4 arguments. It takes a pointer, a size, and that thing, which is weird, and some file. Okay? Let's read about it right here. The function fread reads n MEMB elements of data, each size bytes long, from the stream pointed to by stream, storing them at the location given by pointer. So, 4 arguments. Why don't I just copy this and paste it right here. Okay, so who can start filling out these arguments for me? Avi.
Take out the void. Put just source. Like take out pointer and the star. Put source. Then.
So I'm going to stop you there because that's incorrect. Where should you're right with source, but where should source go?
Put ampers and source.
No, star source.
It should go over here.
Just-
That's the source. Our source is a type. Let's look here. This is asking for a type file star. We actually usually see them like that. So this is asking for an argument of type file stream. That is source, or file star, rather, called stream. That is source. Okay? What size of things do we want to read? I gave you this in the problem description.
1 byte at a time.
1 byte. How big is a byte? Or its size is in bytes, so what can I put right there? 1. Right? That's its size is in unit bytes, so 1 is 1 byte. How many do I want to read at a time?
1.
1 thing. I want to read 1 thing of size 1 byte at a time. And where do I put it once I read it?
Destination.
So I can't put it straight in the destination.
You need to put it
The
into
pointer.
a third point.
To the
Third party.
destination.
Okay, yeah.
You can declare something to act as a temporary storage earlier.
Okay, give me that.
Another file pointer, maybe.
Okay, so this is void star. This is a type void star, so it doesn't have to be a file pointer. And if I'm reading 1 byte, where would be a good place to store 1 byte?
An array.
An array. Okay. And what else is something that's just size 1 byte?
A char. Yeah.
A char star is not 1 byte. A char is 1 byte, right? So let's call this buffer is a generic name used for these things to store something temporarily. So if I create a buffer, right, but it does take a void star, so maybe you are right that it should be a buffer of size 0. So it stores 1, right, because this right here, char buffer is a character, but this takes a void star, a pointer. So I could do this, and now buffer is a pointer. What else could I do?
Put a star next to char.
I could create a char star. Okay. What's another thing I could do? Or let's go with this one, char star buffer. So what do I put in here?
Buffer.
Buffer. Buffer is a pointer to a char, and in that location we're putting 1 byte of something we've read. Yeah, Avi.
Just a quick question. Do you want a malloc buffer?
Who can answer that question?
Well, it doesn't really point to anything right now. So
Wait, but do we want to malloc it?
if you were to do it that way, I guess yeah, because you need to have some place for it to point to.
Do we have to malloc it?
If you're going to use it outside of the loop.
Are we going to use it outside of the loop?
Yes. Wait, do we want to declare it in the loop to begin with?
So I guess we have some pseudo while loop here that we're trying to figure out that we haven't gotten to yet. But so char star, we don't need to malloc it. We're operating in main. It's only going to be used inside this loop. It does not need to exist outside this loop. It can be a local variable. You can have a pointer to a local variable.
But it's not pointing to anything. Right?
No, it's not initialized to anything.
Okay.
But we're not going to use it also. We're going to put something in it the first time we use it. So that seems okay. So we don't need malloc here, and I think it's okay as is. Okay. We have the f read line. Let's do the next line. If we want to write to a file, what is a good function to use to do that?
Fwrite.
Fprintf.
Fprintf is one. What's another one?
Fwrite.
Fwrite. And for our purposes, fwrite, which we saw here, is probably the better choice. It takes 4 arguments as well. Nishant, can you give me the arguments?
The first one's gonna be just buffer.
Okay.
The second one just gonna be 1. Third one's gonna be 1. And the fourth one's gonna be DST.
Does anybody have any questions about that line? That looks good. Okay, so now it looks like the one thing we're missing, or actually let's write this last line, close the files. Who can finish us up writing these last 2 lines? Yeah, sorry, what's your name?
Lucy.
Lucy.
Yeah. F close source and then F close destination.
S close source, open print, source, close paren, semicolon, and F close. It's for the camera. Yeah?
Open parentheses, destination, or DST, and then semicolon.
Great. And what should I include at the end?
Return 0.
Return 0. Do I have to? Do I have to? Just a question. Do we have to include return 0?
No.
No, main does it automatically if you get to the end. But I think it's nice to include it explicitly, especially when we're returning other things throughout the program. Okay, this is what we're missing. While what? Who can think of has some sense of what things could go in there? Even if it's just in some pseudocode-like language. What do we want to go until? Yeah, Lucy.
The end of file.
The end of file. So, what do you mean by end of file?
Like once you reach the end of the file, stop.
Okay, so once we reach the end of the file, How do we know? Great. How do we know when we've reached the end of the file?
I think buffer will be set to null.
The buffer is declared inside the loop.
So you think buffer will be set to null. Why would buffer be set to null?
Because when you do fread, buffer would like, you should try to put nothing into buffer. So, I don't know.
Okay, so you're thinking fread, when we've reached the end of the file, what is fread going to do? I think that's the question we have to figure out.
Yeah.
What does fread do? Does it put null in buffer, or does it do something else? How can we figure out what it does? Man. So let's look over here. Return value. On success, fread and fwrite return the number of items read or written. This number equals the number of bytes transferred only when size is 1. If an error occurs or the end of the file is reached, the return value is a short item count or 0. So for our purposes, if fread reaches the end of the file and reads from the end of the file, there's nothing left to read, what's it going to return?
0.
What?
0.
0. It's going to return 0. So we know that fread, when we've reached the end of the file, is going to return 0. How can we use that to our advantage?
You can declare a variable outside of the loop called like check and like equals for now 1.
Okay.
And then you can put an if statement right after fread. Saying if fread equals 0. No. Like,
Who can help Avi out?
what's the value returned by fread?
We just went over that.
Like, how do you represent it?
So it returns, let's look up here, it returns a size t, which is essentially an integer. So it returns an integer. And in our case, it will return 1 or 0. 1 if it read one thing, 1 byte, and 0 if we've reached the end. So if fread, yeah?
And just put the whole like fread buffer 11 src into the while loop.
So you propose doing this
But then it won't execute a command.
into there.
Will that,
Hold on. Let's. So we're getting rid of that stuff. You're proposing putting fread into there. What should we also move if you want to do that?
The buffer outside.
We should also move this out here.
But does that constantly move it forward? Or actually, no, it shouldn't matter.
Does it execute a command?
No, it shouldn't matter. It actually shouldn't matter.
Okay. So this is what Akshar proposed. We create our buffer. We while fread, then we fwrite. Thoughts on this?
My only question is, would it actually execute the command fread?
Great question. When you're putting a function call inside of a condition, does that function call execute? We have seen examples of this before. And, right?
Okay, yeah, so it does execute.
We've seen things like that before where we have a function call inside of a condition. Does that function call execute? Yes. So the answer is yes, this function call will execute. But again, is it what we want? What is one way we could figure out if it's what we want?
Run it.
Running it?
We could run it. But before we do that, we could also reason through this.
Yeah.
If, say, we have 1 byte in our file, we will get to here. We'll get to this code. This will run. fread will return 1 byte and store it in char, in the buffer, rather. Yeah. And this will evaluate to 1, right? fread returns 1. So while 1, does that mean the code inside the while loop will execute?
Yeah, that's true.
Yes, 1 is true. It's not 0, so the code inside here will execute. So we'll write that. We'll move back to this line once again. Now we have, we're at the end of our file. We read from the end of our file because we only had 1 byte in it. fread returns 0, stores something in buffer. I honestly don't know what it stores in buffer. We could probably look up to see what it does. Not I honestly don't know. We don't know, who cares, what it stores in buffer. But it does return 0 and will while 0 execute. While 0 won't execute, so then we'll move down here.
So it does work.
So let's get a show of hands if this is the code we should run or if we should do changes first. So if you think, you have to vote. If you think we should run this code as is, please raise your hand. Okay. There's one. Do you have a question, concern? Yeah.
Yeah, like after we move like buffer outside of the loop, do we have to malloc it?
Great question. After we buffer outside of the loop, do we have to malloc it? This is a scope question. If we initialize buffer outside of this loop, will it exist inside of the loop?
Yeah.
Yes, its scope covers inside of the loop. So, and really anything below it inside of this code, including the things inside here. So we don't need to malloc it. It's a local variable, and its scope still includes the loop.
Do we need to free it?
Do we need to free buffer?
Yeah, if we don't, right? Because you didn't.
Do we need a free buffer?
No.
We don't. It is, again, it is a local variable.
Yeah.
So we don't need to free it. Okay, let's see what happens. So it is uninitialized. That was something that Marcus proposed earlier. So we have that array variable buffer is uninitialized when used here. How can we fix this?
Malloc it.
Equals null. Say buffer equals null.
Okay. Looks good. We have it now. Let's create something to try copying.
Like a text file.
So we have our text file. How can we run this program? Yeah.
You can do /cp test space test.txt, and then you can name another file which it'll store it into.
Okay, we'll call it out.txt. Cool? Segfault. Thoughts on the segfault? This is great. How can we find out where the segfault is? What? GDB. We run GDB by writing gdb / the name of our program. No command line arguments there. We're going to set a breakpoint at main. If I want to start GDB, what do?
R.
R.
And then
the arguments.
And then what?
The arguments.
Then the command line arguments. Let's walk through. N is just taking me line by line. I'm going to go until I get my segfault. There's my segfault. It looks like fread caused my segfault. I know fread caused my segfault because that was the line we just executed. And the only thing that was happening in that line, two things were happening. Fread was going, and then we were doing some while checking. I'm willing to bet that the while checking was not causing my segfault. Most likely fread was causing my segfault. I also see something here, memcopy. Memory copy sounds like moving memory from one location to the other. Sounds like something that would happen in fread. Maybe some memory moving from here to here. Let's go through this again. How do I start it over and run it again?
wait.
Yeah.
Do you need to put like an ampersand before buffer?
So ampersand before buffer would give me the address of buffer, which is a char star. Let's run through this one more time.
Okay.
How do I run through it one more time?
Just run again.
Hmm?
I think you just type run again.
Just type run again. So we're not going to execute this line. So buffer is a null pointer, correct?
Yeah.
It is a box that exists somewhere, or it is pointing to, let's see, if we have draw a quick picture of this. Can everybody see if I write over here? So in the stack, we have a local variable, and it's called buffer, and it's a pointer to a char. What address is this char at?
0x0.
Right? It's at 0. That's what this is. And in here, inside buffer, is stored 0x0. That's what we have, the setup we have right now. So this line, fread, puts something from source where? Into this box or this box? Which box? Left box or right box?
Right.
This right box. It follows the pointer and puts it in here. When we try and touch memory at location 0, what do we get? A segmentation fault. That's the error we have right now. Yeah?
Don't you have to put star buffer or no for fread?
So fread takes a pointer.
Okay.
And it takes a pointer, so we pass in buffer, and then it'll dereference it somewhere inside fread. But again, we saw it takes a pointer. We don't need to pass it star buffer. That would be passing it whatever's here. And that would probably give us an error because we're dereferencing it. Right? When we dereference this pointer, when we try and access this location, we're getting an error, our segmentation fault. So, oops, we're going to quit out of GDB. Our problem is right here on this line. And it's a problem because of this line. How can we create a box that is accessible when in fread, right? We need to create a box that's 1 byte large, the size of a char, but we need that box to be accessible when this function executes. So where, yeah, any ideas?
You just set it as like any random like character. And I mean like make it okay. You have just do char buffer equals a character. And then when you have buffer there,
wait, char buffer? So no star?
Yeah, take out the star. Equals like a random character.
Okay, so give me one.
It's like A or something. And then when you have buffer there, you use a
Star. Oh no, the ampersand.
Use the ampersand.
Okay, and what about an frwrite?
Use the ampersand again.
Okay, so your idea is we create a char and put something in it, and then write to that char.
Yeah.
What do people think?
It's a bit convoluted.
Okay, let's draw it out. So this time, I'm going to draw this in red on the stack here, and then we will have, oh, sorry. So this time, we have something called buffer, and it's on the stack, correct? And we're saving init A initially. Then we have our call to fread. What fread does is it takes a byte from our file and puts it somewhere. It puts it in whatever the thing's pointing to. Well, before we had this address, 0x0. Now what address do we have?
Whatever address buffer is.
Whatever address buffer is, it's probably going to be something like that. Probably going to start with a B and an F, and then have 6 other hexadecimal digits. Doesn't matter. Some address, and we're passing that address in, and we're going to put our 1 byte thing at that address. So we're going to put our 1 byte thing inside here. And then we're going to write from whatever inside here. Does anybody have any questions about that? Who thinks this code will work? Raise your hand if you think this code will work. You have to take a stance. And who thinks this code won't work? Raise your hand. Everybody else should be raising their hand. Okay. Michael, where are you standing?
I can't decide. Kind of in the middle.
You're in the middle. Pick one.
I'll have faith and say it will work.
Okay, you'll have faith and say it works? What happened?
You didn't enter your
Oh.
arguments.
No seg fault. How can we check to see if 2 things are equal? 2 files are equal.
Diff.
Diff checks for the differences between 2 files. And if it returns nothing, they're identical. And if we open up, we get our file. So that was the correct solution. Let's look back at it one more time. We actually didn't even need to initialize it, and it would probably look a bit cleaner if you didn't put something random in there. The point being, you needed to create some space to store something from fread and take something out of for fwrite, and that thing had to be either a local variable on the stack. You could have malloc some space. So we actually could have written malloc here, and that would have worked. And then we would have been storing our thing somewhere on the heap. But this is actually probably the most elegant solution. Just create some space on the stack for these things to go. I would have two other comments. If you were to turn in this and then get scored on this, my comments would be as follows. These ones here, to me, look like magic numbers. This one, in terms of fread, makes sense. That's the number of things to read or write. But this one right here should probably be something else. So what is one solution?
Size of byte.
Like that? Size of char. Yeah, byte is not a type. So size of char works. We could have, at the top of our code, hash defined. That. Called something byte, and it's really a char. Actually, an even better approach might have been this. Uint. Anybody know what that is? Or sorry, I have it backwards. Wait, no. Which way does it go? It's the other way. My bad.
No, you had it right.
Anybody know what that is? Yeah.
It's supposed to help like standardize across systems things that have unsigned integers that have 8 bytes.
That's exactly right. It is, on different machines, the size of a char, not usually a char, chars are usually 1 byte, but the size of other data types are different sizes on a 32-bit machine versus a 64-bit machine. A uint 8 _ t is always 8 bytes, 8 bits rather, always 1 byte. And I need to include that standard int header file. So now, this would have probably been the best way to write this code. So I get rid of the magic numbers, and I also have a more logical type for buffer. It is not simply a char. It is a byte, which is what we expect it to be. And up here, we've actually been a bit more robust. We're not calling it a char, which maybe, who knows, could be a different size on different machines. We're actually saying this is exactly 1 byte, always, no matter what. And if we look here, we make CP. Uh-oh. What happened?
It might be switched.
What?
Is it?
You didn't define it as a type.
But it should be defined in standard.
What's going on?
Did you include?
Should define be all caps?
So it's not sharp defined. Actually, in this case,
It's type def?
Yeah.
we're going to use type def.
Yeah.
Because we're using it as a type in one location. So in this case, we actually want a type def byte. We're creating a new type byte, and it is essentially this. It's a bit different than sharp defined. And now, our code works perfectly. So again, sharp defined takes something, replaces it everywhere with the other thing. It's just a macro shorthand to get rid of magic numbers. But in this case, because we're using it as a type right here, in order for that to work, we need to type def whatever byte is. And we're defining it right here. It's not a struct. It's actually just an unsigned integer. It's 1 byte long. This code will be available online, and you all should have it right now. So we have perfect 13 minutes left to go over problem set 5. I want to walk through copy.c together, and then we'll talk briefly about the other parts of the problem set. So let me pull up copy.c. It should be my downloads. Oops. And the cool thing is we've actually already written a lot of this code. We pulled the code, the code we wrote, it literally just came out of here when I was writing this on my own. But this is copy.c forms the foundation for the first two parts of the problem set for whodunit.c, which you need to write, and resize.c. Recover.c, which is the third and final part of the problem set, is not based off of this file. You're going to need to write that file. We give you a template for that file, but it has nothing to do with copy.c. But because copy.c is the foundation for the first two parts, we're going to walk through it now so you have a good sense of what it does. And the comments give some of it away. We've already written some of this. First, we're making sure we get 3 arguments. Next, we're remembering the file name. So we skipped this step when we coded our thing, when our CP. But here, they're making it a bit cleaner. They're checking to make sure both files are good in addition to opening them. We wrote all this code just now, so I'm not going to dwell on this code. Next is some stuff that's specific to the types of files we're using, which are bitmap files. Bitmap files have some metadata associated with them. So the first couple of bytes tell you about the file. They aren't the colors of the pixel in the image. They tell you about the file. And if you read through the problem set, you'll have much more information on what types of metadata structures are included with bitmaps. But that's why we have this first set of this code right here. We are reading the metadata, 2 pieces of metadata, the file header and the info header. And we are checking some parts of it to make sure it is a true bitmap file and before continuing. And again, these are details we don't need to go into now. If you read through the problem set, you will understand these. Long story short, these are just saying this is a bitmap file and confirming that. Next, we're writing those to the out file. We see that here. We're writing to the out pointer. Next, we're determining padding. So again, this is a particularity with a bitmap file. Some lines include padding at the end. And if you read through the problem set, you'll learn more about padding. This is the formula to find padding. Important to remember, when you change the size of a bitmap file, the padding changes. When you change the size of a file, the padding changes. It's never going to be greater than 3. It'll be 0 through 3 inclusive. But when you change the size of something, the padding changes. If I only have my size of my pixel, if I only have 1 pixel in that row, I need 3 pixels of or 3 bytes of padding, because each row has to be multiples of 4 bytes long in a bitmap file. But if I double it to go from 1 pixel to 2 pixel, each of which, let's say, is a byte, then I need 2 bytes of padding to make that equal to 4. So when I change the size of something, I need to change the amount of padding I have. Does that make sense to everyone? Next, we iterate over each row, or through all the rows, and then we iterate through each column in each row. We're treating this bitmap like a grid, like we've treated the board in 15, like we treated the bricks when we printed them on the screen. A grid of rows and columns. Then we saw this. We actually just coded this. We created some temporary storage. We read in there, and then we write it out. This is exactly what we just did. Next, because I said each line ends in some padding, we skip over that padding, the old padding, and then we add it back. In this case, we're creating the same exact file. We're just copying it. So this line is kind of silly. We could literally just put the padding in. But if you change the size of the file, do you still want this line? So if we change the size of a file, do we still want to skip over the old padding?
Yes.
So we do, because this, again, deals with the source file. We don't care about the padding from the source file. We want to go to the next line. But we don't simply put back the old amount of padding. We need to put back the new amount of padding. So when we're changing the size of a file, we still want to skip over the padding in the old file, what we're reading in from. But what we're writing to, we're going to need to put back some different number of padding that we've determined. Yeah?
The order of those 2 lines doesn't matter, right? Because you're handling different files.
Exactly. The order of these 2 lines does not matter. We write this line, This is here for the file we're writing to. That's important, so we get the right amount of padding. This is for it has to deal with the in file. We want to skip over the padding. We don't want to read. If we're reading a byte at a time, we don't care about those padding bytes. We want to move to the next line. Finally, just like Lucy gave for us, we close the files and return 0. So this is copy.c. And we actually we spent most of section writing this, essentially. You made this, so hopefully you have a good sense of what's going on in here. The big difference, honestly, is just this first part that deals with peculiarities of bitmap files. So I have as my next slide, what do we need to do? Well, let's think about whodunit. And for somebody who read through the problem set, what do we need to do in whodunit? Simply, Aleja.
So we take out the part of each pixel that denotes red, and then kind of.
OK. So take out the part of each pixel that denotes red. That's close, but not all of it.
Well, there's different ways to do it.
OK, give me one
Take
way.
out all the red and then emphasize the blue and green.
OK. So given both these ways, it sounds like given a pixel, it has a red, blue, and green level. We want to change the relative levels of the red, blue, and green, depending on that pixel. Where in this code should we change the relative red, blue, and green levels of a given pixel after we've read it before we write it? Give me the line number.
83.
83. So right here. For whodunit, the code you need to write should all go right there. And that's the only code you need to write. Because like we heard, all you need to do is change these relative blue, red, and green levels from each pixel. You've read it in, and now you're going to write it out. How do I get, if I have this thing called triple right here, and it's of type RGB triple, well, if we looked in bmp.h, what is RGB triple?
It's a struct.
RGB triple is a struct. We see that right down here. And so if I wanted to access, say, the red level of the struct, how do I access the red level of this struct?
RGB triple dot RGBT red.
Like triple.
Is that correct?
Should be like a triple dot instead of RGB triple dot.
Triple. Triple is the local variable, so here there's no pointers here, so we just use the dot notation. This will give me the level of red. If I want to change it, I just set it equal to something different. So again, this line of code accesses this variable inside this struct, and we can set it to something new. So for whodunit, again, this is, in essence, what we need to do. Very simple. Just change some relative levels, and this is where that code goes. Resize, on the other hand, is a bit trickier. In fact, resize is probably the trickiest part of this problem set. We have 3 minutes to go over it, but again, we've already written most of this code, so we should be pretty familiar. What are some things we want to do in resize if you've read over the problem set? If you give them to me, we can talk about them. What are some things we want to do?
Vertically, so you have to horizontally resize it, but vertically resize it as well.
So if we're given a pixel and we want to resize it by a factor of 2, it now needs to be resized horizontally and resized vertically. Does that make sense? Yeah. So we can. That's probably the biggest challenge, and we'll talk about that in a sec. Yeah.
I mean, the way I thought of it was you needed to print it out.
Wait, don't tell us what you did. We're gonna talk. We're gonna talk in logic.
Okay, like, what was the question?
You just raised your hand. There was no question.
Okay.
Let me present that. Let me just discuss this briefly. So we have one pixel. We want to replicate it both horizontally and vertically. So ideally what we do here is we read in our pixel. We write it however many of times. But then we have our trick here because then we want to like skip to the next line and write it at the beginning of the next line. So if we want to replicate both horizontally and vertically, what is one good way to do that? One good thought to do that. So we don't need to constantly seek around our file to place the things. That question might not have made sense, but I think an answer to it will help clear it. So let's think of each file as a row. Let's think in terms of rows. If we have our first row from our small picture, we can make that row into a large row from a large picture and then replicate that row however many times it needs to be replicated, rather than going pixel by pixel, which gets confusing when dealing with files. Because if we had, I'm running out of space. If this is our file and we have that one pixel there, and we want to put it right there, we still have some things that need to go over there when we're writing and creating our new file, our file that's twice as big. But it's really hard with file functions to skip around to new lines like that and then go back here and put things in there. It's almost impossible to do something like that, if that makes sense. So if we think in terms of rows, we can take our row and then put it, replicate rows vertically, and that's how we deal with resizing vertically rather than horizontally. That was kind of quick and a little confusing. Unfortunately, our time is up. I will stand outside for those of you here who have questions about the problem set, including Recover. So let's adjourn for now. And again, if you have any questions, we can chat outside.